Welcome to your lesson on potential difference, current, and resistance. It's going to be a short one. You already know this. The device that supplies electrical energy to an appliance is called the source. And you already know, I'm sure, from elementary school, that we can have hydroelectric dams supplying that, a wind turbine, solar panels. We can burn fossil fuels. We can use batteries like a dry cell. As far as your house goes, your electricity comes from your outlet, which ultimately comes from one of these sources. Now, when we are describing potential difference, we are really talking about voltage, okay? Voltage, potential difference is exactly the same thing. Potential difference is just talking about the amount of energy between the 2 points, and voltage is the fancy term named after the guy who did a lot of work on it. So you could have different voltages. An outlet in your house is 120 volts. If you were to be overseas somewhere, you'd probably find 220 volts or 240 volts come out of European sockets. The normal little battery, just like this one here, is 1.5 volts. That's why sometimes you need multiple batteries, because sometimes you need to have, 6 volts. So then you'd need 4 of these batteries in your device and whatnot. So just the voltage is what is the push that drives the electrons through a particular load. And so some require more voltage than others. Okay. Now, in a normal plug, the wider part, if you've noticed that in our plugs in North America, you got a wide part, that's the positive terminal. And then the short, smaller one is the negative terminal. This is a safety feature to make sure that when you plug in your device, you're always plugging it in so that the current flows in the correct direction. This one here, looks like a little face with a mouth, but this one here is your ground plug. You don't have any electricity flowing there. It's there for safety. So for example, if your device was made of metal and a wire got loose on the inside, it may touch the outside of the metal, and then there would be electricity conducting. So basically, if the wire inside was attached to your metal chassis, in that case, electricity would flow, but instead of flowing through you, it would take the path of least resistance, which would be to the ground wire, which is attached somewhere to the body of the metal thing that you're using. So this is a safety feature on a lot of our things. That's why some devices, like Christmas lights, they're not carrying a whole lot of voltage. You're not too worried about getting zapped if a wire comes loose. So they may not have a ground pin, but a lot of devices with higher voltage will. It's a safety feature. Okay, so again, what is potential difference? What is voltage? Well, it's the difference in electric potential energy between 2 points in a circuit. And I'll show you down below what I mean when I say that. Remember that it is measured with a voltmeter, and the unit is volts. We use a capital V, must be capital. And of course, the circuit symbol is a capital V as well. So here's how charges, well, it's a cartoon way to show what's happening here. First, you get a charge carried up very easily. You get some charge separation. Imagine you got a little guy inside the battery, and he carries it up and he places it on the top shelf. And he can do that over and over and over again, placing them on the top shelf. That for this little guy to pull the electron up to the top, he's going to need a lot more strength because these positive charges are tugging on that electron. It's going to be very difficult to steal any more electrons. So eventually, the traction between the positive and the negative charges is too strong, and no more negatives can be separated. That's when you've got your maximum use out of a battery. Okay, so the potential difference across the battery represents the voltage. Now, when you're adding and testing a voltmeter to your circuit, you have to do it in parallel. You don't place voltmeters in series. This would be incorrect. You don't want to put it in line with the flow of electrons. You want to test the difference between this area and this area. You want a voltage drop. So you're going to test what's called across the battery, testing across the battery or testing across the load. You must have a separate parallel pathway so that you can test to see the difference between the voltage here and the voltage here, because the force is going to be different inside here. It's going to be using some of that voltage as it's passing through. Okay, so please make sure whenever you're drawing your voltmeters, you must add them in parallel. So we move on to current. Current is the flow of electrons. You should know this already. It's moving charges. It's how many charges pass a point in a second. So when we're thinking about it, I want you to actually think about the idea that electrons are bumping each other in a wire, and that's causing electrons to move through the wire. Now, if you've got a lot of charges, then you have higher amperage. So 3 units of charge versus 1 unit of charge. Very simple, okay? Obviously, this is just, again, a cartoon way of thinking about it, but that's the idea, all right? Now, ammeters, when you add an ammeter in, it has to be in series What do we mean? We mean that it has to be in the same pathway as whatever you're trying to test. It must be in line. And that's because you want to test the current. The flow of electrons through the ammeter in this wire will be the same as the flow of the electrons through the light and the flow of the electrons through the battery. So you want to make sure that it's in line. It must be connected in series. Okay. Now on our diagrams, if you see these dots here, really that just means that there's some kind of a connection. So the wire that was connecting to the battery had a separate little node or connection there. Same thing with the light. There was a connection on the light and then another connection on the other side of the light. So again, in series, not in parallel. Only voltmeters are added in parallel. Okay. Finally, we have resistance. Now resistance is when any kind of load, so any kind of substance, pushes back or opposes the force of the electrons moving through it. In other words, it's like you're pushing on somebody and then they are putting on the brakes and it's hard to push them. And the more a substance resists that the force of the electrons being pushed through it, the more it can convert the energy. So electrons coming into a load are going to collide with so much force that the electrical energy can be converted to other forms like heat or light. So the more resistance it has, the more energy that substance gains from the electrons passing through it. And that energy, you can't just store energy forever, that energy is going to get radiated to the surroundings as either heat or light or whatever kind of energy you're trying to convert it to. But heat and light are pretty common. Okay, we measure that with an ohm meter, and the unit is an ohm. We use the Greek letter omega as the unit. And so you'll see this quite a bit coming up. Voltmeter to measure volts. An ammeter measures amperes or amps. And an ohm meter measures the resistance in ohms. Here's a brief little idea of how light bulbs are actually working. So when a light bulb has the electricity coming into it, the little thin piece of metal that makes up the filament of the light bulb is actually a pretty poor conductor. So that when the electricity comes up and through, and notice that I've connected it on purpose to the side and to the bottom of the light bulb, that's where the two connecting points are. As you go up and through and you change into this resistant material, you're going to get a lot of conversion into light and heat. This is an incandescent bulb, so we get a lot of heat out of it as well. The difference between a bulb like this and some of your fluorescent bulbs or your LED bulbs is that they are much more efficient, and instead of wasting the electrical energy as heat, they are able to convert most of it, not all, but most of it, to light instead. Whereas these incandescent bulbs, they can heat up pretty badly. It's a bit of a waste of the electrical energy if you're creating heat when all you need is the light. So anyway, that's the idea. Resistance in the filament causes the filament to heat up and glow. That's the same thing that's happening inside your toaster. When you have your toaster has little thin strips of metal. If you looked inside your toaster before, you've seen them light up red. And those are the filaments in there that are resisting the electricity as they're running through. The difference here now is that the toaster is actually wasting energy as light because it should all be going to heat. So it's kind of the opposite problem that a light bulb has. One final reminder, the increase or decrease in the energy of a unit of charge, so that in other words, between one point in the circuit and another point in the circuit, how much that load has used that energy is called potential difference. It's the difference between two areas. The voltage can be used to describe how much electrical energy got lost by the load. So how much energy was actually converted to light and heat. Then we lost that on the way back in. Okay? And that's why we call it a voltage drop. That's why we test across a load in parallel, because I want to know the difference between this point and this point. How many volts were used by that particular resistor? And that, my friends, is the end of your work. You've got some worksheets to do and some textbook homework. If you have any questions, let me know.